Hello everybody, so for lesson one of our lockdown, we're going to be going through the structure and the properties of different chemicals and looking specifically, the property we're going to be looking at is the melting and boiling point. So as it says there, you're going to need the following. You're going to need your key area 2 book, you're going to need your data book, pen and a pencil, and then maybe some paper to write on too. So if you don't have those, if you can pause this and then just go and pick up those things. Now, as we go through this, we're going to have some prior knowledge questions to get you started. And those are really, really important that you complete those, so you can pause the video and then come back to the answer afterwards. You can go through this at your own time, and then we've also got a corresponding worksheet which you'd be expected to submit as soon as possible. Okay, so once you've got those things, let's get started. So this is just a little bit of revision about rates of reaction, so pause the video, and once you've got your answer, then we can go through. So to work out the rate of the reaction, we have to work out the change in quantity divided by the change in time. So the quantity here is going to be the volume is changing, so the volume of carbon dioxide is changing. At 8 minutes, the volume is 82 centimeters cubed, and at 2 minutes, it is 52 centimeters cubed, so the difference there is 30. Our time, our change in time is 8 minus 2, which is 6. So our calculation is therefore 30 divided by 6 equals 5 centimeters cubed per second. So the answer is therefore A. Let's move on to the next one. Okay, so pause this if you need, and then you can come back to the answer in a few seconds. So if something is an ion, it means it has a different number of electrons to the number of protons it has, and if it's negative, it means it's going to have more electrons than it does protons. So we are looking for, let's have a look here, it can't be B because we have the same number of electrons and protons, so that must be an atom. C is the same. D has more protons, so it's got more positive protons than negative electrons, so that would be a positive ion, and therefore the answer is A, because we have one more negative electron than we do positive protons, therefore this is a negative ion. Identify the particle which would give you a lilac flame colour. So you're looking for the flame test section of your data book, and the answer for that would be potassium, which has an atomic number of 19, so therefore the answer is D. Let's move on. So this is the most relevant to today's lesson. So could you pause this, have a go at the answer, and then check your answer in a few seconds. So the dot and cross diagram for water is shown as there. And it's really important as well, which I think would be beneficial for today's lesson, is to get this definition of what a molecule is, because we're going to need to know that. And a molecule is a small number of non-metal atoms that are covalently bonded together. So these two chemicals here, we've got hydrogen fluoride and water, they're both classed as being molecules because they're non-metals, and we also have a small number of those atoms joined together via covalent bonds. So these are two different molecules, and that word will be important for today. So here's what we're going to cover. We are going to be looking at the structure of different chemicals and then their properties, and the properties we're going to focus in on today are the melting and boiling point. Your success criteria are there, so just have a read of those, and when you're ready, let's move on. So the kind of questions that you can expect to see and the kind of questions you're expected to answer are the following. So read this. I don't expect you to get the right answer, but this should hopefully get your brain ready to answer these style of questions. And then again, another type of question that you'd be expected to see here. So read this, please. So in this question, we're looking at the structure. What is the structure of silica? It gives you something called a chemical formula there. We have a melting point, which is quite high, and we'll hopefully by the end of this lesson going to be able to deduce what the structure is based on the melting point, and then explain why it has that melting point. Okay, so we have three basic structures for our different chemicals, for our covalent and ionic chemicals. If we have an ionic chemical, which is non-metal and metal ions bonded together, then they're going to form this lattice structure, which is going to be trillions and trillions and trillions of all of these ions, negative and positive ions, which are all ionically bonded together. Our second type of structure is if we're looking now at covalent chemicals, we can get two types of covalent structures. We can get something called a covalent network, and in a covalent network, well, they're all going to be non-metals, and in this case this is looking just at carbon, so this is the diamond structure, or structure of diamond rather, and all of these grey black dots, those are carbon atoms, and the red lines are covalent bonds, and each carbon atom is bonded to another carbon atom via a covalent bond in one huge structure. So this picture here is a very, very small representation of what the actual structure would be. It would be much, much, much bigger than this. Again, it would be trillions and trillions of these atoms depending on the size of the chemical that you're looking at, the size of the diamond that you're looking at. We can also have a third type of structure, so the second type of covalent chemical. And this is a covalent molecular structure, whereby here we have, well, we defined the word molecule before, didn't we? We said it's a small number of non-metal atoms. So this here is an example of water. Water would have a covalent molecular structure with the individual water molecules. And we're going to look at each of these structures now in a little bit more detail. We're also going to answer, how does that structure there affect the melting and boiling points? So here's your first little task. If you can go to page 37 in your book, and using page 5 and page 9, can you complete the table? This is just a small version of this table, but can you complete this table in your books? So pause the video when you're ready. And then also I want to have see if you can answer this question here. Is there a pattern to the type of bonding and the melting and boiling point, which we've abbreviated to MP and BP? So pause this, go to page 37, use your data book, and when you've completed the table, unpause the video and I'll show you the answers. So if you want to pause this and just check and see how you've got on, please. If it's a non-metal, it's going to be covalently bonded together. If it's metals and non-metals, it's going to be ionically bonded together. And hopefully you found all of those melting and boiling points in your data book. And in terms of a conclusion, we should have found that all ionic chemicals are going to have high melting and boiling points. In this table here, the lowest melting point for the ionic chemicals would be lithium bromide at 550 degrees Celsius. Whereas the covalent chemicals are a little bit different. Some of them are really high. For example, silicon dioxide has a melting point of 1713, whereas nitrogen, which is also covalently bonded together because it's non-metals, two non-metal atoms, has a melting point of -210 degrees Celsius. So there's quite a big difference there. We've got very low for nitrogen and very high for silicon dioxide. So what we're going to do now is hopefully try and explain why there is a big difference between those melting and boiling points. So if you look at an ionic lattice, it's not just one or two ions. As I said before, it's many, many of these ions all ionically bonded together. And if you want to melt that, you have to break all of those individual ionic bonds. So ionic bonds are very, very strong. So it's difficult to break one ionic bond. But because there's so many of them, you have to have lots and lots and lots of heat energy to break all of the ionic bonds. So the diagram there on the right, that represents the ionic chemical in a liquid form now. Whereas on the left-hand side, that represents it in the solid form. So here's a little summary of that there. Read this, please. So we need lots of heat energy to break all of those ionic bonds. And this is shown by a high melting and boiling point. So sodium chloride, which has the chemical formula of NaCl, has a melting point of 801 degrees Celsius, which is very high. And it's very high because of the reason there in the sentence above. Our next structure is the covalent network structure. So in this here, I said before, this is what diamond looks like if you can zoom in on the atomic scale. And again, if you want to melt this, you have to break all of those individual covalent bonds. So on the right hand side, it represents it in the liquid form, and on the left hand side, it represents it in the solid form. And this is difficult to do, to break all those covalent bonds, for a very, very similar reason to the ionic lattice. So have a read of this, please. And our evidence for this is in the melting and boiling points of the covalent network chemicals. So an example would be silicon dioxide, which is a covalent network. that has a melting point of 1713 degrees Celsius, and that shows just how difficult it is to break all of those covalent bonds. The covalent bonds are strong and there's lots of them, therefore we need lots of heat energy. Our third structure is the covalent molecular structure. So a molecule there, let's define it again, is a small number of non-metal atoms covalently bonded together. We have a molecule here shown of water, of H2O, and that's an individual discrete molecule. But if we have a glass of water, for example, we're not just going to have one molecule, we're going to have many, trillions and trillions and trillions of these molecules, and they will all interact with each other. So the dashed line there that is interacting with, it is showing between the molecules, is what we refer to as a weak force of attraction, or an intermolecular force of attraction, and it's very, very weak. So I'm going to zoom in now just on two water molecules there, and if the dashed line there, again, that represents our intermolecular force, our weak force between the molecules. The solid black line within the water molecule, well, that is a covalent bond. It's the covalent bond between the hydrogen and the oxygen. But when we melt this, so on the left hand side it represents it as a solid, on the right hand side it represents it as a liquid. When we melt this, that intermolecular force, that weak force, is broken, and it's not difficult to do. So have a read of this here, please. So the reason why some covalent chemicals have very low melting and boiling points is because you're not breaking covalent bonds, you are only breaking weak intermolecular forces. And it's why, for example, that water has a low melting and boiling point of 0 degrees Celsius, whereas silicon dioxide, as we had previously, has a high melting point of 1713 degrees Celsius. What's important to note here is that when you melt a covalent molecule, you don't break the covalent bonds. So some people think that the bottom section here is actually what goes on when you melt a covalent molecule, which isn't the case at all. So the left-hand side represents it in the solid form, and then the bottom right-hand side represents what some people think. Some people think that the strong covalent bonds between the atoms are broken, but this isn't the case. What is happening is that the weak forces are broken, which is why they have low melting and boiling points. So your next task, please, is to complete the table on page 41 in your notes. It's a summary of what we've just gone through there. You can have a look back through your notes and have a read. And if you can pause the video, and when you're ready, we can go through the answers. So have a look at this here. Hopefully you've got all of this correct. If you've got anything wrong, don't worry about it. You can correct your answer. So pause this, mark your own work, and then we will move on. So that's the lesson over. We're going to have a couple of past paper questions just to help you out. So we've stated the name of our ionic and covalent structures. We have an ionic lattice, we have a covalent network, and we have a covalent molecular structure. We've explained how the structure determines the melting and boiling points. The ionic lattice and the covalent network structures have high melting and boiling points because you have to break lots of strong ionic or covalent bonds, whereas the covalent molecular structures have low melting and boiling points because you only have to break the weak intermolecular forces. So let's have a look at some questions, this kind of thing that you may be assessed on in your exam. So as before, please pause this and then we can go through the answer when you unpause it. So we have four structures there. The question is, which of the following diagrams could be used to represent the structure of a covalent network? Well, the top one we haven't actually come across before. That's what's known as a metallic lattice. The next one below, we have negative, so B, we have negative and positive things. Well, hopefully you identify that as an ionic lattice. C, we have individual things. We have the two atoms joined together in what's known as a diatomic molecule. So this is a molecular structure. Whereas down at the bottom, D, we have our covalent network structure. So D is the correct answer. Next question. So again, just have a read through this here. I'm going to give you a little clue, but if you want to pause the video now without the clue and have a go at the answer, now's the time to do that. And here we go. So this now is your little clue if you wanted. So if you remember when we talked about the covalent molecular structure, there are weak forces between the molecules, and that's what's being broken. So pause this and see if that helps you out a little bit. Okay, so let's go through the answers. So the bonds between the molecules. So between the molecules, that's known as the intermolecular forces. Well, they're very weak, and that's the thing that is broken during melting. The bonds within the molecule, well, that's a covalent bond. That's the bond between the hydrogen and the oxygen, the solid black line, and that's very strong. So our answer is weak at the top and then strong at the bottom. Next question. Have a read of this, please, and then pause it. And if you wish, you can wait a few seconds and I'll give you a clue. So here's your clue here. This is our structure here, and this is silicon dioxide. So what structure does this look like that we just previously looked at? Okay, so this is known as our covalent network structure. And that's it in terms of the past paper questions. In your worksheet, you may get some questions similar to this here. So this is a framework, if you want, for how to answer the questions that you may be given. And this one here is explain the difference in melting point of sodium chloride and ammonia. And it gives the melting points there, 801 degrees Celsius and minus 78 degrees Celsius. So our structure would be, could you state the melting points of both? Could you then state the structure of both of these chemicals? Could you explain what happens when both of these chemicals melt? And then could you state the relative strengths of their structures? So I'd like you to prepare an answer for this. So pause the video, use that framework there, see if you can hit all 4 of those points, and then I will give you my version of the correct answer and you can reference that against yours and see how you've got on. So pause this. I reckon this should take you about 5 minutes or so, and once you're ready you can have a look at the answers. So here, what I've done here is I've stated the melting points of both of my chemicals. I've then stated the structures. Next, I have said what happens when those chemicals melt. And lastly, I stated the relative strengths of my structures. So again, just pause this and see how you got on with all of these here, please. So that's us completed the first lesson. If you can get your corresponding worksheet to your teacher as soon as possible, we can mark that and get you some feedback. And then next week we will go on and look at a different property. Okay, so thank you for getting this far. And if you've got any feedback for how we can improve these, please let us know as soon as possible. And if you're struggling with anything, if you've got any questions, let us know too. Get in touch via email and we will help you out as soon as possible. Okay, thank you.